Statsproblems.com was used to create this tutorial, which can help us calculate an independent measures two-way ANOVA, but with less calculation than a complete test because the sums of squares are given. Let's begin by selecting one of the 25 example problems. The question appears in the blue box. A set of population scores is normally distributed. Compare the means of a 2 by 2 ANOVA. Total number of scores, NG, is 16. Number of rows, R, is 2. Number of columns, C, is 2. Sum of squares row, SS row, is 460. Sum of squares column, SS column, is 470. Sum of squares within cell, SS within cell, is 960. Sum of squares total, SS total, is 2050. Alpha is 0.05. What are the results of the hypothesis tests of this 2 by 2 ANOVA? Let's step through the solution by clicking on the Next Step button. In Step 1, we calculate the sum of squares of the interaction term, SS int. Sum of squares interaction, SS int, equals sum of squares total, SS total, minus sum of squares row, SS row, minus sum of squares column, SS column, minus sum of squares within cell, SS within cell. In this example, SS int equals 2050 minus 460 minus 470 minus 960, which works out to 160. In Step 2, we calculate the degrees of freedom. R is the number of rows. C is the number of columns. The degrees of freedom row, df row, equals the number of rows, R, minus 1. In this example, df row equals 2 minus 1, which works out to 1. The degrees of freedom column, df column, equals the number of columns, C, minus 1. In this example, df column equals 2 minus 1, which works out to 1. The degrees of freedom interaction, df int, equals the number of rows, R, minus 1, times the number of columns, C, minus 1. In this example, df int equals 2 minus 1, times 2 minus 1, which works out to 1 times 1, which works out to 1. The degrees of freedom within cell, df within cell, equals the total number of scores, ng, minus the number of rows, R, times the number of columns, C. In this example, df within cell equals 16 minus 2 times 2, which works out to 16 minus 4, which works out to 12. In Step 3, we calculate the mean square terms, ms row, ms column, ms int and ms within cell. The mean square row, ms row, is equal to the sum of squares row, ss row, divided by the degrees of freedom row, df row. In this example, ms row equals 460 divided by 1, which works out to 460. The mean square column, ms column, is equal to the sum of squares column, ss column, divided by the degrees of freedom column, df column. In this example, ms column equals 470 divided by 1, which works out to 470. The mean square interaction, ms int, is equal to the sum of squares interaction, ss int, divided by the degrees of freedom interaction, df int. In this example, ms int equals 160 divided by 1, which works out to 160. The mean square within cell, ms within cell, is equal to the sum of squares within cell, ss within cell, divided by the degrees of freedom within cell, df within cell. In this example, ms within cell equals 960 divided by 12, which works out to 80. In Step 4, we calculate the observed f values. In a two-way ANOVA, there are 3 hypothesis tests and therefore 3 observed f values. The observed f value for the row effect, f row, is equal to the mean square row, ms row, divided by the mean square within cell, ms within cell. In this example, f row equals 460 divided by 80, which works out to 5.75. The observed F value for the column effect, F column, is equal to the mean square column, MS column, divided by the mean square within cell, MS within cell. In this example, F column equals 470 divided by 80, which works out to 5.875. The observed F value for the interaction effect, F int, is equal to the mean square interaction, MS int, divided by the mean square within cell, MS within cell. In this example, F int equals 160 divided by 80, which works out to 2. In step 5, we find the critical F value. In a two-way ANOVA, there are 3 hypothesis tests, and therefore 3 critical F values. We need alpha level and degrees of freedom to look up the F critical value. There are 3 hypotheses, row, column and interaction, to test in a two-way ANOVA. The alpha level is 0.05 for all 3 hypothesis tests. In the F table of critical values, the column of the table indicates the numerator of the F ratio, and the row of the table indicates the denominator of the F ratio. Each hypothesis test has its own degrees of freedom for the numerator. For the test of the row effect, the degrees of freedom in the numerator is degrees of freedom row and the degrees of freedom for the denominator is the degrees of freedom within cell. For the test of the column effect, the degrees of freedom in the numerator is degrees of freedom column and the degrees of freedom for the denominator is the degrees of freedom within cell. For the test of the interaction effect, the degrees of freedom in the numerator is degrees of freedom interaction and the degrees of freedom for the denominator is the degrees of freedom within cell. In a 2x2 ANOVA like this one, the degrees of freedom for all 3 effects are the same, so we only need to look up one critical F value. Use interactive table 8 to find the critical F values. Using the alpha equals 0.05 table, with df numerator of 1, df for row, column and interaction effects, and df denominator of 12, df within cell, for all effects, to find the critical F value of 4.75. We close this window to return to the analysis, which shows that the critical value from the table of 4.75 for all 3 tests. In step 6, we test the hypotheses for all 3 effects. For the row effect, the observed F value of 5.75 is greater than or equal to the critical F value of 4.75, so we reject the null hypothesis for the row effect. For the column effect, the observed F value of 5.875 is greater than or equal to the critical F value of 4.75, so we reject the null hypothesis for the column effect. For the interaction effect, the observed F value of 2 is less than the critical F value of 4.75, so we fail to reject the null hypothesis for the interaction effect. In addition to the 25 example problems, we can work step by step through an unlimited number of new problems using the Generate button. The Edit Data button can help us create problems with customized input. Instructors can use this function to create problems with complete solutions to use on exams, in class or for homework. For printed output, we can print the question. Or we can print the question with the complete solution. You can also work out the complete two-way ANOVA with scores as input, but this problem solver takes a very long time to work out with so many steps. The free website has statistical analyses in all of the most common areas in statistics. Statsproblems.com also has a mobile version so you can access the site from anywhere. For help with statistical concepts, HelpMeWithStats.com is a free website that has more than 70 tutorials, as videos, or as self-paced slideshows. In addition, HelpMeWithStats.com gives you free access to a comprehensive stats textbook with more than 685 review questions. Thanks for watching. If you find these resources valuable, please share statsproblems.com and helpmewithstats.com with your friends and instructors.